In the previous session, we all have started working on variational autoencoders. So we will be having a quick look about what variational autoencoders were, which we have coded yesterday, followed by understanding the reparameterization trick and the encoder and decoder model, which we have instantiated. Followed by we are going to implement the plot model, which we left yesterday, and we will continue from there. And finally, we will be testing our model. Okay, so let's go for it. Now here, so yesterday we have started working on autoencoders. In order to perform or in order to create the autoencoders, we have implemented the following. We have used the following libraries: the input dense lambda, model MNIST. We have taken some loss functions like binary cross entropy and mean squared error. Along with, we have used this function plot model, which we will be using today. Along with, we have used the matplot library for plotting the graphs. Then we have read the MNIST dataset and we have reshaped the dataset so that we can start processing. Along with that, we have initialized the network parameters where we had the input share of 784 neurons. Along with that, the intermediate dimensions which we have selected was 512 neurons. Followed by, we have taken a batch size of 128 along with latent dimensions for our sample Z. We have taken it as 2 and the number of iterations will be 50. Then we have created a variational autoencoder using the encoder and decoder model. So the encoder has been defined here where we took an input shape. This input shape is of 28 cross 28 pixel size, which is 784. Followed by, we have taken the dense layer with two 512 neurons with rectified linear units activation. Along with that, we have defined the latent dimensions of the two-dimensional variations which we will be generating. So first we have taken the Z mean and we have taken the Z log variance. I've already explained in the previous video that how we are using mean and the standard variance or the covariance in order to quickly identify a controlled sample, and using that controlled sample, we can perform variational autoencoding. So in order to generate the sample, we have defined a method known as sampling. Within that sampling method, we have received the Z-mean and the standard covariance. Along with that, we have got the shape, we have got the dimensions, we have calculated the epsilon, and finally we have returned the sample Z. So the sample Z will be a return of Z-mean plus Z-log variance as well as the inputs, whatever has been given. So we have got this factor return Z-mean plus exponential of 0.5 into Z-log variance into the epsilon. Then we have made use of reparameterization trick so that back propagation is possible in our neural network. And once the back propagation is possible, we will be able to calculate the partial derivatives from the model also. Okay. So we have named it as Z, the sample which has been identified. Then we have created an encoder model and we have to plot the encoder, which we will do today. Along with that, we have created a decoder model and we have initialized the decoder model also. For the decoder model, it was very simple. Decoder model is responsible for variance, but in general, the decoder model is not self-sufficient in generation of variations because of intractability and less control. So in order to make control, we have to identify a lower bound. And in order to identify the lower bound, we have introduced the encoder model with the decoder, and we have made it as variational autoencoder. So using this decoder, we will be generating the variational images. We have initialized the decoder model. And finally, after initialization, we are going to make the plot and we are going to call our function with which we will be calling our VAE and all that stuff. Okay. So we have started defining a method known as plot results. So let me do one thing. Let us just define this method a little up. Okay, command Z. It would be better if we can define it just after the sampling. Go to the sampling and define after sampling. You can define your plot models. We are defining it in advance so that the functions gets initialized and we will be able to execute these functions well at the bottom. So we have defined this function plot results, which is going to receive the models, the data, batch size, and we have provided a temporary model name, that is variational autoencoder for MNIST dataset. Okay. Now from this models, we will be receiving two information, the encoder model and the decoder model. Okay. So let's take the encoder and the decoder model will be extracted out of the models which we will be receiving. We are going to pass it as an array, pass it as a list of encoder and the decoder, and we are going to receive that. So once we have received that, we are also going to receive the data. That this data will be the testing data over which we will be plotting. So we have taken the X test and Y test. We are going to receive the information from the data. So we will be receiving two arguments, one for models, another for data. And the data will be the test data and the models will be the encoder and the decoder models which we have created. Along with that, for specific models, we can generally create the directories so that we can create images for variational autoencoder, mean variance, and whatever outputs we want to generate. So here is a new concept which you guys will get introduced to. The plots which we will be generating today, we will be exporting the images of that graph also so that we can utilize those images in our research in order to understand how the mean variance has been explained. So in order to do that, we have already done import of OS here at the top. Okay, we have not imported that. So let's do one thing. Let's import OS. Okay, and let's initialize all these. So I'm just initializing my libraries and I have imported the OS. Okay, so we got the OS. Let us just initialize the data also. So we have imported the MNIST dataset. Along with that, let me initialize the network parameters. And this variational autoencoders and everything we will be calculating once we are done with defining our plot test. So now what we are going to do, we will be exporting our images in a directory. So let's just make a directory using the library OS. And within the OS directory, we do have a function make directories. And for this, we will be creating a directory with a model name. Okay, so we have defined the model name at the top. Okay, so similarly, you can quickly take up the model names. Okay, so here I think I have taken the model, so you can rename it to model name. So once you are going to get the directory, okay, so we can quickly have a look. We can quickly check in case if the directory exists, then we are not going to generate, we are not going to create the directory. If the directory exists, you can mark it as true. So the directory won't be made and the old directory can be used. Now, similarly, once we are done with creating the directory, let us just quickly export the file. So we are going to make use of operating system. We are going to get the current path. We are going to join the current path with the model name. So we are going to get the directory like VAEMNIST directory. And within that directory, we are going to export the variational mean.png. Okay. So whatever mean errors we will be calculating, we will be exporting all that mean results into a PNG file. Okay. And let us just quickly export that file as the file. Okay. So this is going to be the file that will be generated. Now what next we need to do? Let us just predict using the encoder model, and let's calculate the Z mean. So we have received the encoder, and using the encoder, we are going to perform a prediction. The prediction you have already done previously. So for prediction, we'll take the test case, and if you want to define the batch size for faster processing, you can define the batch size information, which we have taken at the top. Now, once we are going to perform this prediction, we are going to get three information: Z mean, log variance, and the subsample. So I will be only taking the mean, and others, we are just going to save that into these underscores. So as you already know, in Python, the underscores just hold the last value of the calculation. So we can quickly put the values into these underscores. We have to provide this, otherwise you can save it onto a variable also, but this underscore variable is by default defined in Python, hence we are going to store in that. Otherwise unnecessary space would be taken in case if you initialize a new variable, and there is no way that we cannot define it, because once we are going to predict using the encoder, all the three things which we are generating, which is the mean, the log variance, as well as the sample, all three will be exported. Okay, so we are just storing that into zmean, and once you have got that, let's make the plot. Okay, so in order to make the plot, let's make use of our matplot library, plt.figure. Now in the figure, you're going to define a figure size, and let's say the figure size would be, let's say we're going to take something like 12 cross 10. Okay, so we are going to have a width of 12 along with the height of 10 pixels. Okay, so what do we exactly want to do? We want to create a scatter plot, and what the scatter plot will do, this scatter plot will display the mean on the x-axis. There will be two columns for the mean, which we are going to get. We are going to get all the rows, the values for the x-axis and the values for the y-axis. So we will be defining both of these values in the scatter. So on x-axis, we are going to take the mean from the column number 0, and on the y-axis, we will be taking it from column number 1 of the Z mean, which we are going to generate. And if you want, we can quickly have a print of Z mean so that you guys will be able to understand what we're exactly taking in. Okay, so we are going to create a plot. We're going to create a figure of 12 cross 10. Now we're going to create a scatter plot. Now in order to take the scatter plot, we're going to make use of this value Z mean. We are going to fetch all the rows using the slice, and we'll read that value from column number 0. Okay, so we are going to get the mean value from column number 0. Then we want to represent the information for column number 1, which is the next feature, and that will be displayed for all the number of rows. So let's say I'm going to take the Z mean, and for all the columns, then we'll be taking it from column number 1. Okay, along with that, you can define the value of any color sequence or anything. If you want to define, you can use a marker color. Okay, so in fact, you can actually use your test set, the Y set, in order to define the color sequence. So we can also do that. So we are going to get a multicolor graph, so that Y test will be represented with a random color here. So I have defined a Y values, the testing Y will be represented with a color. Now once we have got the scatter plot, you're going to create a color bar. So in Python, we do have a color bar also that will help you understand the legends kind of information. Okay, so we're going to make use of color bar also. Now once we have got that, we are going to get two values. So let's say we are going to have the labels on the x-axis. So for this, we are going to display the sampled information from row number 0, and for Y label, we are representing the information for column number 1. So we are going to define somewhat like that, Z of 1. Okay, so relevant values you're going to see, sorry, this is the Y label. For X label and Y label, we are going to define this information. Finally, you're going to save the file. So you can use the save figure and you can define the file name which we have generated above. So our image is going to be saved onto a directory, which we can use it for further purposes. And we are going to show the graph. Okay. So once we got this, now what we are going to do is we are going to generate the digits over the latent information which we have got. Okay. So there will be another plot which we will be generating along with this plot results, and that is going to be the variational digits which have been generated. Okay. So for that, let us just create another file name. We're going to create another file name using os.path.join, and we are going to define it as under the directory model name. We are going to define, let's say, digits with latent variable that will be generated over here. We are going to create a PNG image. Okay. Now, let's say we are going to get a 30 cross 30 two-dimensional manifold of digits. Okay, so n number of elements which you want to take up, you can create the matrix. So let's say we are going to take 10, like the way we have been taking earlier. Okay, you can use any number here, 10, 20, 30, 40, up to 60,000. You can take any values. Okay, so we have got this. Along with, we have the digit size information, which is the 28 pixel. So we got the images of 28 cross 28 pixels. So we are going to define that our digit size is 28 pixel. Okay. So let's just increase some number of some numbers here. We'll be taking 30, let's say. Okay. So that we'll get a big image along with some different number of variations for different number of digits which have been taken. Then what we are going to do, let's just create a figure with initialized with zeros. So by default, we are going to create an image filled with zeros. Okay, that is, it's going to be a blank image, a black kind of image we're going to generate for the digit size into the number of elements which we will be defining here. So let's just take the digit size. Okay, and with respect to digit size, we are going to multiply that with n number of elements which we are defining it. Along with, we will be having a square matrix where we are going to have the same number of elements in the rows and same number of elements in the columns. So we are going to get a figure filled with zeros. So this is going to be a blank image filled with zeros. Okay. Now we are going to fulfill the information so that we can represent our information within that figure. So for that, what do we need to do now? We are going to create a linearly spaced coordinates corresponding to the two-dimensional plot of the digit classes in the latent space. So for that, linear spacing coordinates, in order to represent that in a two-dimensional plot for the specific information available with the latent space, we have to make use of linear space. And we are going to create a linear space of 4 cross 4 for n number of elements. So we are going to take a grid, and this grid would be somewhat like x and y. मतलब दोनों एक्सिस पे हमें एक ग्रिड बनानी है, और उस ग्रिड को हमें लीनियर स्पेस के थ्रू हम उसको क्रिएट करेंगे. एंड फिर उसके बाद में हमारे पास जो भी ग्रिड की इंफॉर्मेशन होगी उसमें से रीड करके अपना डिकोडर यूज करके हम एक रैंडम वैल्यू जनरेट करेंगे इमेज की, और वो वैल्यू जनरेट करने के बाद हम अपने फिगर के अंदर, जो ऊपर हमने फिगर बनाया है, उस फिगर के अंदर हम उस वैल्यू को इंसर्ट करते जाएंगे. तो फाइनली क्या होगा, हमारे पास एक ऐसी इमेज जनरेट होगी जिसमें वेरिएशनल नंबर्स, हमें डिकोडेड वेरिएशनल नंबर्स दिखाई देंगे. ओके, सो फॉर दैट व्हाट वी आर गोइंग टू डू, लेट्स जस्ट मेक यूज ऑफ linear space with np. So here is the method linear space which we can use. So what linear space can do, it will return evenly spaced numbers over a specified interval. Okay, so we are just taking an interval, let's say from starting from -4 to 4, we are taking a common interval, and we are defining that for n number of elements, 30. Okay, so that this information will be represented as a simple grid x. Okay, post that we are going to read the same number of elements and up to the index -1, because now we will be reverting the order so that we are going to get the y based columns created for the grid. So we are going to take grid and we are going to define the linear space. So once we define the linear space, again we are going to define 4 cross 4 n, but this time we are going to pass in certain parameters. So let's say we are going to pass in up till -1. So how do we create these grids? I'm going to give you a session on that. Let's say in the next session, maybe, wherein you will understand how we generate all these dynamic grids. Okay, but for now, just you make use of the code that we are going to create a grid space from -4 to 4 along with a value. So we are going to get a grid. So a grid would be nothing, just like a blank figure kind of image. And within that grid, we will be representing certain number variables. And these number variables will be modified in order to show the variation of the characters which we will be creating. So once we are done with creation of the grid, now what next we are going to do? Let's say we are going to enumerate each value in the grid y, as well as we are going to enumerate each value in the grid x. And for the values of yi and xi, we are going to create an array, and we are going to save that into samples. And then using that sample, we are going to perform the decoding process. And once whatever the digit has been identified after decoding, we are going to represent that digit information in that figure. So for that, let's just quickly start by creating a loop. So let's say we are going to take the value first for y. So we are going to get two values, I and index of I in the grid y. We are going to take this. We are going to use the enumerate function so as to enumerate all the elements from the grid. So this is also like an iterable, wherein you can extract the elements of grid from the y-axis. Then we are going to get the another element j for the index xi, or let's say for the index I in column x. Okay. So we are going to enumerate that, and we are going to pass the value of x. So we have got both the grids red, and these grids are nothing but some random variables using which we will be actually creating the inputs, an input matrix, which will be used for decoding, which will be used for prediction. So now what we are going to do, let's just make an array. So we are going to make an array, and within this array, we are going to pass in an object, and this object is going to be a list object where we will be representing the xi information and the yi information. Okay. So we are going to get an array or a list like object. So I've passed the list like object, and this object is going to represent a z sample. Okay. So once we have got that z sample, we are going to perform prediction using the z sample. So we are going to make use of the decoder. We are going to perform the prediction. In order to perform the prediction, we are going to make use of the z sample, and let's just save that into a variable, let's say x decoded. Okay. So we have got the prediction of the samples. So whatever samples we have taken from the grid, we are going to perform the prediction on it. We are going to get the decoded value. So this is something like f function of x using z, and z here is the sample or the latent variable which we are taking. Now, once we have got this decoded values, we are going to fetch the rows and columns. Initially, we are going to fetch that. Let's say we are going to fetch the rows, and we're going to reshape it. Okay, and using the digit size, the 28 cross 28 pixel, we would like to read digit size. Okay, and once we have got the first element out of the x decoded, let's just save that into digit. Okay. So once you have saved that into digit, what next we are going to do? We are going to create our figure. So in the figure, now we are going to perform some changes, and we are going to insert the values into the figure for x and y. So let's say we are going to have a product with I. We are going to read the digit size. Okay. And we are going to read it for the elements I plus 1. Okay. This is a simple list comprehension kind of we are implementing here into the digit size. Okay. So we are going to fetch that value. Along with that, we will be having the jth value also. So we are going to read the digit size for the values of j plus 1, okay, and we are going to print the digit size. Okay, so we have got the final digit created. Okay, so this information will be extracted from the digit we have extracted from the previous session, previous variable. So now what you're going to do, you have decoded, you have predicted the value, you have decoded that into a digit, and now that information out of that digit will be actually stored over the figure which we have created above. Okay, here I think here we have created that figure with zeros. So we are going to fill these values, okay, which we have created here. So now once we have filled those values, we are going to perform the plot. We are going to calculate the plot, or we are going to draw the plot. So again, we are going to draw the plot with the variations of numbers here. So let's just plot a figure, and we're going to define the figure size. Let's say this time the figure size could be 10 cross 10 for this. Okay, you can take any value. It will automatically adjust on the basis of your screen. Then we are going to take a floor division of digit size. So in order to take a floor division of digit size, we're going to digitize it. We're going to get the starting range from where we have to display the pictures, and we have to calculate an end range also. So in order to get the end range, we are going to get the last value. So to grab the last value, we are going to get that value from n minus 1 cross digit size for the number of digits available, and we are going to grab that from the start range plus 1. So this is going to be our end range. Let's just save that into end range. Okay, so once we have calculated the start range and the end range using np.arange function, what we can do is we can define this start range and end range in order to generate the pixel ranges, and these pixel ranges will be displayed over your plot. So what we can do is we can take two options. We can take a pixel range, we can take a sample range as well. So sample range we will be taking from the grid, and pixel range we will be taking from this using the np arange by defining start range and end range, and then we are going to make a plot. So once you have got the end range, let's just quickly calculate the pixel range using the arange function available with np. So arange will return evenly spaced values within the given interval, and the interval will be the start range and the end range which we have calculated. So let's define the start range and end range. Okay, and here we are going to define the digit size as well. So for each digit size after 28 pixels have been read, we are going to take it as another image, and we are going to define the pixel range this way. So this will be the pixel range for each image object which we will be taking up, and there will be the sample range for x and y, so that we can take from the grid which we have already created above. So using the round function, we are going to actually make use of grid x, and we are going to get that up to 1 decimal position. Okay, so we are going to round that, and once we have rounded that, let's save that into the sample range x. So we have got that into sample range x. Along with, similarly, we are going to round the grid y up to 1. np.round, use grid y, round it up to 1, and save that into a sample range of y. Okay, so we have rounded the values of the grid, the x and y, and once we have got that, you can also define the labels as well. Let's just call it as plot x label, and you can define, this is going to be your z of 0, the z labels, and then we will be having the y labels. This is going to be your z labels of 1 which we have taken, the values for 1, and then we are going to show the image. So let's use plot.imshow. Once you have defined plot.imshow, we are going to define the figure. Okay, and you can define the variable color map here, cmap you can define. So you can define any, like here the images of the MNIST data set is gray images. So we have to provide a color map as grays. So there is a value here which we can use grays underscore r, which is going to give you the grayscale images so that you can represent them in IST images appropriately. Finally, we are going to save the figure and we are going to define the name of the file, which is going to be our digits with latent variable.png file, and we are going to show that image. Okay, so somehow like this we have created the plot results. So what we are actually trying to do, we are trying to make two plots. One is the plot with the mean variance, the mean absolute mean squared errors. Mean, actually we are trying to represent that information for that mean sampled which we have generated, and depending on that we are actually generating another, the variation of digits with the latent variable z, which we have been using. So using this, we have enumerated the grids, we have extracted the combination of sample grid, and using this sample grid, we have decoded. So we are going to receive some linear spaced information for the grid, and for that the prediction will be done, and once the prediction will be done we will be decoding it and we will be using those values in order to update our figure. So once we got the figure updated, we are going to read the values from the figure and we are going to display the values over our page. Now, once we're done with that, finally, let's just call the boilerplate code in order to call our all these methods and functions. So let's go to the bottom and let's just define our calling code. So now here we are going to define a main method. This is going to be our main function. Okay. And in the main function, okay, so we have defined our main function. Now with this main function, what we are going to do, we are going to receive some information. First we have to pass the information to the model. So let's say ऊपर हमने एक मॉडल्स पास किया है अपने प्लॉट करने के लिए, तो हम मॉडल्स ले लेते हैं. मॉडल्स में हमारे पास क्या होगा, वी आर गोइंग टू हैव अ सेट ऑफ एनकोडर एंड अ डिकोडर. ओके, ये हमारे मॉडल्स हैं, एनकोडर मॉडल. एक हमने डेटा वेरिएबल पास किया था ऊपर. तो डेटा वेरिएबल में हम टेस्ट डेटा सेट दे रहे हैं, एक्स टेस्ट एंड वाई टेस्ट. कैलकुलेट हम ऑलरेडी कर चुके हैं, बट ये हमें ऊपर प्लॉट में पास करना है. सो मॉडल्स एंड डेटा ये दोनों हमने डिफाइन कर दिए हैं. अब इसके बाद में आपको क्या करना है, अब आपको कैलकुलेट करने पड़ेंगे आपके लॉसेस, और वो सब लॉस पहले आप कैलकुलेट करेंगे. लॉस कैलकुलेट करने के बाद वेरिएंस वेरिएशन ऑटो एनकोडर लॉस आप कैलकुलेट करोगे. फाइनली हम अपना मॉडल डिस्प्ले करेंगे, मॉडल जनरेट करेंगे और उसे प्लॉट करेंगे. ठीक है. सो पहले आपके पास एक मल्टी लेवल परसेप्ट्रॉन प्लॉट होगा. उसके बाद में फिर हम मतलब अपने मॉडल को ट्रेन करके एनकोड कर देंगे, जिसमें एरर रेजोल्यूशंस के बाद में जो भी मेन वेरिएंस होंगे उन वेट्स को हम सेव करने के बाद में फिर दोबारा अपना MLP मॉडल ट्रेन करेंगे और उसको रन करेंगे, प्लॉट करेंगे रिजल्ट्स को. ओके, सो लेट्स गो फॉर इट. सो हियर व्हाट वी आर गोइंग टू डू, लेट्स जस्ट call the binary cross entropy. Okay, we're going to call this function binary cross entropy. We're going to take the values inputs and outputs which we have defined above. Input and outputs. I'll just check if my variables are correct. Inputs and outputs. I've got, yeah, I've taken inputs here for the encoder, and I would have taken outputs here. Okay, here it is, outputs. Okay, so I've got binary cross entropy, inputs and outputs I'll be taking. I'll be calculating the reconstruction loss using binary cross entropy, and let's just save it as reconstruction loss. Okay, so once you have created the reconstruction loss, we are going to multiply the reconstruction loss with the original number of dimensions so that we will be able to calculate our further loss like the divergence loss and the total variance autoencoder loss. So there are two types of losses which we have already discussed yesterday. One is the reconstruction loss of the image, and second is the divergence loss, the KL divergence loss. And variational autoencoder loss will be the combination of both the losses, the reconstruction loss as well as the divergence loss. So once you have calculated the reconstruction loss, we are going to calculate the reconstruction loss for the original dimensions, and the original dimensions was 784, 28 plus 28, which we have defined. So let's just multiply that. So reconstruction loss will be your reconstruction loss into your original dimensions. Okay, reconstruction loss into original dimensions. So we calculated the reconstruction loss. Similarly, we are going to calculate our KL divergence loss. And in order to calculate the KL divergence loss, we have the equation which I have already explained you yesterday. We need to calculate the log variance and define it subtracted by the KL divergence. So we are going to make use of square from the Keras, and we are going to calculate the square of mean. Along with, we are going to calculate the negative of k dot exponential of the log variance. Okay, so z log variance. So you can refer the previous article which we have referred in the previous video yesterday. So you will get to know the KL divergence loss equation from that article, and you can define this equation. So we can save that into something like KL divergence loss. And once we have got this KL divergence loss, we are going to take a sum of the KL divergence loss along with the -1 axis, let's say the reverse axis. So in order to do that, let's just define K sum. We're going to take the sum, and here in the sum we are going to make use of the KL loss which we have defined in the previous row, previous statement. So once we have calculated the KL loss, you can quickly define the axis of calculation of the loss. So axis should be -1 here. So axis, what it represents, an integer, a list of integers, and here the rank has to be provided in the negative format. Okay, so it sums over all the dimensions. So we have to pass it with -1. Okay, so we are going to use the KL loss here, KL underscore loss. This is going to be our summation of the KL loss calculated over from the axis -1. And once we have got that, we are going to multiply that with -0.5, which is in the equation. So here we are going to calculate the KL loss. So you can actually define KL loss is equal to KL loss into your -0.5. Okay. So once you have got this values, we have got the KL divergence loss along with the reconstruction loss. So when we add up both of them, we are going to get the variational autoencoder loss. So we're going to take the mean value of both the losses so that we are going to get an average mean of the loss. So we are going to get the reconstruction loss, and we are going to calculate plus we are going to calculate our KL loss. Okay, so we have got both the reconstruction loss plus the KL divergence loss. So finally, we are going to add the loss into our variational autoencoder model, which we have created above. So depending on that loss, the variations will be introduced in your variational autoencoder, and your new images will be generated. Okay, so over this model, we are going to add the loss. So once we add the loss here, we are going to get the variational autoencoder loss added. So let's add the loss to the variational autoencoder model, and let's compile the variational autoencoder model. So for compilation, here there is an optimizer which we can use. Optimizer, it's not taking, okay, I'll just define it myself. Optimizer, and here we can take the Adam optimizer, the default optimizer for variational autoencoder as per the document which we referred. So they have already defined the compilation optimizer should be the Adam optimizer, and we are going to get the summary of variational autoencoders. Okay, So once we are going to get that, now we are going to train the autoencoder. We have got the train summary. Let's just train the autoencoder. So in order to train the autoencoder, we are going to define, let's call it as the function fit, variational autoencoder.fit, wherein you're going to provide your training data. You have already defined the network parameters above. So we are going to define number of epoches as number of epoches we have defined above. Along with, we have the batch size. We have already defined the value for the batch size above in the previous cell. So we have taken the batch size. Along with, you need to have the validation data. So the validation data will be your test data. You can take it X test. Along with none, we have to define it. There are two, you can pass X test comma X test both ways, or else you can only call X test and you can define the another one as none. And finally, we are going to grab the weights. Okay. So once you have grabbed the weights, you can quickly check the weights calculated, what weights have been identified with the variational autoencoder. So there is a function here from the variational autoencoder model where you can save the weights using save weights function. And the weights are generally stored in the H5 file, H5 format file. So you can make use of these weights in order to export the model, and you can use the weights to regenerate other models and other variations. Okay. So let's just save the weights, VAE MLP dot MNIST dot H5. Let's say we have saved it with the name variational autoencoder with multi-layer perceptron for the data set MNIST, and the format is H5. So this is going to be saved in the current directory. Once our variational autoencoder has been trained, now we are going to plot the results. Okay. So to plot the results, we're going to define the models which we have taken from the above. We're going to define the data which we have got. We're going to define the batch size as the batch size which we have already defined above, and we're going to define the model name. So the model name which we're going to define will be a variational autoencoder with multi-layer perceptron. Okay, you can define any way model. So this is how we have got the final plot ready, but we want to create two more plots here. So for the decoder, which I have told you yesterday, for the decoder as well as for the encoder, which we have created above. So let's plot the decoder model. So in order to plot the decoder model, we are going to make use of the function plot model. Okay. Using this plot model function, you have to define the model and the file to which you want to plot the model for understanding. So let's say we are going to define the decoder here in order to plot the model, and we are going to define name. So you can take this attribute to file. Okay. So once you took the information file, let's call it as VAE decoder.png. You're going to get the decoder. Okay. As well as you can show the shapes of data. So show shapes can actually is by default false, so you can use it true. So within that PNG file, you will be able to see the decoder information also. So that's how you can plot the model. Along with that, you can plot the encoder model also. So you can use plot model. You can simply pass the decoder, the encoder. Once we have got that, we can save it to a file, and we can export that to VAE encoder.png. So these will be the models which will be exported in a PNG file for references, and we are going to define the shapes as true. Okay. So if you want to refer, so what we have done, we have defined the following. We have got a plot results method, which we have actually defined here. Okay. And we have plotted the results. Along with that, we have got the variation autoencoder model. One more thing we can do using the plot model which we have created, we can also export this complete variation autoencoder also. So as we have exported the encoder and the decoder above with the plot model, we can also plot the complete VAE in a PNG file also. So we can define the plot model, we can pass the variational autoencoder, and we can also export that to a file, and this could be our VAE. Okay, encode decode.png. We can export that also, and let's just show shapes equal to true. So once we create the variational autoencoder, we have created a simple encoder, we have created the simple decoder, and in the plot results, we have generated some random samples, a grid of values, and using that grid of values, we have actually predicted the variables. And once we have provided these arbitrary Z samples, we have decoded these Z samples. And once we have got these Z samples, we have plotted them over the figure. Okay. So that's how we actually implement variational autoencoder. So now let's just quickly check back if everything goes well. We are going to get that executed. In case if there is any error, we are going to check back. So I hope you all are done till here. Let me just quickly run that. Okay, so by the time it runs, you can quickly see that we have got an encoder here. We have got a decoder model here. Now we are training for the samples for the number of iterations. So we have defined 50 iterations here. And here on the left-hand side, you guys are going to get your encoder, decoder, PNG files also. Okay, so by the time it get trained, let us just show the encoder PNG. We have got a decoder PNG also. And we have got the complete variational autoencoder. Okay, so here, if we go here, here variational encoder, we have got an encoder image. So here is your encoder. It looks somewhat like this. We have got an input of 784. We have got an output of 784. We have created a dense layer of 512. Then in the encoder, we have actually calculated a Z mean and we have calculated the Z log variance. Okay. And finally, we have created a sample Z with a lambda function for the provided mean variance. So that is your encoder model, which has been generated. So with respect to the diagram which we used yesterday, accordingly, we have created the encoder. Similarly, we have plotted the decoder model also. So here is the decoder where we are taking the sample values. Now using the sample values, we are creating a dense layer to generate 512 features. And out of that 512 features, we are finally creating 784 features. Okay. So once we are done with that, we have got the complete encoder and decoder model ready. So here is our encoder model. Okay. Input layer, the encoder model, and the decoder model. So you can use these encoder and decoder models for reference. Once, let's say you will be presenting somewhere, you can make use of how you have used the models and how many neurons you have created on each layer. You can define that information. Along with that, once our number of iterations will be done, you are going to visualize a mean graph here that will be plotted, which we have created in the plot results. And second will be our variational images, which have been created with the numbers. Okay, so by the time it gets loaded, in case if you want to see any line of code, just let me know so that I can show you that. So we have just plotted, and I hope you all are comfortable with how to generate the plots with matplot and with this. So just a few mathematical libraries you all need to explore, like the linear spaces, some of the functions which may seem a little new to you. So you all can quickly make use of it, and a way of reading the values. So these are the two things which you all can see. Otherwise, everything is pretty easy. So we just created an empty zeros. We created a linear space for a range. Then we enumerated all the values and we decoded it. And finally, we have updated the figure. And once we have updated the figure, we have got a pixel range and we have plotted the figure. That's it. So it's pretty simple actually. And now here we have got a mean variance graph. Okay. So here there are two samples here. So you can quickly observe here at the very bottom here, we have got certain number of values. So by default, you can see now we have got the variations of the images. So here are the two axes. This is the axis Z of 1 and this is the axis Z of 0, which is represented. Okay. So let's say an image of 7 has been taken. Okay. So an image of 7 has been taken, and on x-axis there were certain variations which has been introduced, and 7 could be represented as 1, and on y-axis there were some variations where the 7 has been tuned into be represented as 9, later it was represented as 4, and finally it was represented as 0. And these are the possible number of combinations that what can be generated. So you can see that using 9, 3 has been identified, using 4, 2 has been generated, then 6 has been generated, then 5 has been generated. So there are a lot of variations which has been generated using the variational autoencoder. So I hope this is clear to you that how variational autoencoders actually work, and depending on the inputs, depending on certain variational inputs, we can actually generate variational outputs. Okay. So this variational autoencoders are pretty important. And here you have a graph representing the squared errors. So here you can see that different sections are representing different patterns of information. So let's say here you have a color green. So this green color is represented here on the color bar, which is somewhat near to this, which may represent 7. Along with that, at the very bottom, we have the value zeros as well on Z of 0. So here it's the value of 0. Okay. Then we have got the values of 1, which has been generated along with the variations. So you can see that now, depending on the respective values in which direction we are moving. Okay. So let's say if we are moving from 0 towards this direction. So generally what we are getting, as well as in case if we are moving from 0 towards this direction. Okay. So if we are moving in that direction, we are actually receiving the values as 7. And there are certain other values which have been generated. So you can see that these are some combined error patterns and the variation patterns which have been generated here in this section, because this area also represents a value between, let's say, 4, and it also represents a value somewhat like 8 and 9. Okay. So since in the graph we have generated 9 out of 4, or else you can say 4 out of 9. So hence we have got a mixture here. Otherwise, all these mean information are represented differently. So this shows that given some number of inputs, and if we varies in 2 directions along with the x-axis and the y-axis, there will be different patterns generated, and the patterns will be variable in nature. Okay. Now I've got a few comments. Let me see. I'm getting error in this line. Grid Y. Okay, disregardable. Okay, fine. Okay. So with this, we have actually generated the variational autoencoders, which can instead of reconstructing the image, can actually reproduce the images. Okay. So if you want to see any line, just let me know on chat. I can help you with that. And we are getting, okay, list index out of range on line number 81. Okay, so you are trying to pass the encoder along with the inputs. With that too, you have passed the decoder. You have uh, okay, and then you are passing that. Actually, there are two differences. One, on 81, 82, you are trying to use output, and you're calling another in the variation encoder model. So one is output, another you have defined as outputs. So just change output on line number 81, one to outputs. Okay. Second, we have to check back. You may be getting an error with respect to the encoder as well as the inputs. So I think inputs you have already calculated within the same cell. Otherwise, what you can do is just simply run these previous cells, because it may be possible that the input shape would not have been taken, hence it may be showing the list range out of error maybe. So you can quickly run the cells from here, from the import statements, along with reading the data sets, initializing the network parameters, and then just run it. So first, on line number 81 and 82, there are variations in the name outputs. So you can change it to outputs on line number 81. Second, you can quickly check back if you have called all the cells appropriately above. Okay. So once your encoder will be initialized, there won't be any problem. Otherwise, on variational on line number 82, you have got the decoder encoder inputs and the variational model along with inputs, outputs, and name variation autoencoder. So that's fine. Okay, you ran all the cells. Okay, maybe you would have. So I'm okay. You are getting that error because check on line number 81. You have created the variable as output, and on line number 82, you have created a variable outputs. You have used the variable outputs. So both has to be same on line number 81 and 82. Have you updated that? Just update that and then run. Okay. So that's how we can create the variational autoencoders and run all again, fix same error. Maybe you would have missed something, because I cannot get to know with your line sequence that why it is not taking list of 2, because that's appropriately correct. And I think on the chat what you have shared me seems pretty similar. You have taken the encoder of inputs and you have taken 2 out of it. Okay. You've got a decoder, stored that into outputs. Inputs, outputs, you have got encoder. Index error, list index out of range. So it is saying once you're trying to read the encoder inputs, it is not able to read the index number 2. Okay. But that is not possible, because if you print inputs here, we have taken that with a specific input shape of 784. Okay, that is our encoder input which we have taken. So, and once we have used the encoder here, you can also check line number 64 if you have appropriately initialized your encoder. So we have taken the inputs here along with the mean and the log variance and the sample Z. Then using that encoder, we are calculating on line number 81. First, we are encoding the inputs and then we are decoding it into outputs. Okay, maybe there could be any small issue like any text issue maybe. That's why it may not be running. So what I can do is I can quickly share my script with you and you can check back and just identify what could be the problem. I think it would be a any minor issue would be there. Okay, so you can quickly refer to my script and you can just check back. No, I didn't change anything in my code from yesterday. Just one change I have made, the change to outputs. That's it. Okay, so I've shared the code. You can quickly have a reference. Now let's have a look. So we have imported the few libraries here. Along with that, we have taken the MNIST dataset. We have reshaped it for processing. We have defined the network parameters as input layer was 784, dimensions were 512. The intermediate dimensions along with the latent variable which we are creating is of 2 dimensions. We will be creating it, we'll be taking 2 axes, z of 0 and z of 1 to introduce the variance. Along with that, we have created a simple encoder. The encoder had 1 layer. Then we have created the samples using the article which we referred yesterday, how to create the mean log variance, and along with the values of epsilon and the exponential, we have calculated the value of samples. Once we have got the samples, we have defined a function for plotting the results, and for plotting the results, we have just defined a grid, and within that grid, we have defined some empty values. Then we created a linear space from the values -4 to 4. And for all those random variables, we have decoded the elements, and once the elements have been decoded, we have updated the values after decoding into the figure, and we have plotted the figure on a ratio of 10 cross 10 where we represented the values of latent variable z on along with column number 0 and column number 1, and we have performed those variations. So for that, we have used the reparameterization trick. For that, I have already shared the resource with you yesterday in the previous session. So in case if anybody has not referred previous session, they can watch out the previous session where you will be able to understand all these technical aspects of reparameterization and how we are taking the reconstruction loss and the variation loss and the variational autoencoder loss. So this part, the reconstruction loss, the KL divergence loss has been defined within that article. Along with that, the variational autoencoder loss is a combination of both of them. So once we have calculated the loss, one thing we have to do here is, in order to introduce the variance, we add the loss to the model. So with respect to the loss added to the model, we are going to introduce certain variations. And once the variations has been introduced, we are going to train the model, and finally we are going to plot the results. And once we plot the results, we are going to get the models generated along with the number of iterations. And once the iterations has been done, we have got these figures which actually represents different number of characters which has been taken from inputs and the values generated. Along with the variations, this is the image which actually represents different variations along with your axis on z and z of 0 and z of 1. Okay, so that's how we generate variational autoencoders, which are generally used to enhance your data set. So if you have some n number of images, you can actually create variational images using them, and using those variational data sets, you can improve the quality of classification. This is one kind of application which can be done. Generally in the industry, generative adversarial networks are also used. They are considered to be a little better than variational autoencoders. And using generative adversarial networks with the existing patterns, you can regenerate new patterns. So this is like artificial intelligence has become that creative that if it learns some basic fundamentals, it can connect those fundamentals in order to regenerate or in order to generate future creations. Okay. So as we have also seen certain examples of the person does not exist and the paintings and the music examples which have been generated with artificial intelligence. So in the next session, we'll be taking up the concepts of generative adversarial networks, the real GANs. You are going to generate GANs, okay? And for that, I would like to recommend you all to go through with all these previous sessions, try to implement each line of code, and I would recommend that execute each line of code in your own script, try to print the value, and just try to match and understand what output you are getting, okay? So in the session, due to time limitations, somehow we are not able to explain each and every part and we cannot show that. So it's your responsibility to take up each statement and just print those statements just to understand that what is happening. So you have to execute the script again, step by step you have to execute. While executing each line of code, just test that line of code and understand what is the output, how is it represented, and then you will be able to understand this concept a little better. Moreover, I would recommend you to go to the previous session also. Uh, Read the articles which I have shared with you yesterday. Those articles have very nice information available. So that will actually help you implement all these equations and understand the relevance of the equations which we have implemented today. Okay. So that's all for the session. Rest will be talking about generative adversarial networks in the next.